A soda comes in many flavors, varying levels of sweetness and caffeine. A soda is not a soda without the fizz. Like other carbonated beverages, the fizz in soda comes from carbon dioxide gas dissolved in it. Carbon dioxide is carbon with two double bonded oxygens on either side. Keeping carbon dioxide gas in solution is a delicate process. Carbon dioxide gas above the soda creates pressure on the surface of the liquid, which prevents carbon dioxide dissolved in the liquid from escaping the liquid. The carbon dioxide gas above the liquid and the carbon dioxide gas dissolved in the liquid are in a dynamic equilibrium. Meaning carbon dioxide enters the liquid at the same rate that carbon dioxide exits the liquid, and the concentration of gas in the liquid and above the liquid do not change. The focus of this simulation will be on the solution's equilibrium. In soda, the carbon dioxide gas dissolved in the solution is undergoing a chemical reaction where it combines with water to form carbonic acid. CO2 plus H2O yields H2CO3. This reaction is reversible, meaning that the carbonic acid can decompose into carbon dioxide and water. The reaction is happening in both directions all the time. When the system is at equilibrium, the rate of the forward and the reverse reaction is happening at the same time. So the concentration of CO2 and H2CO3 remains constant, not equal, but constant. The system stays in a dynamic equilibrium until a stressor is applied. We are going to be applying different stressors to the system. We're going to be changing temperature, pressure, volume, and we're going to see which way the system shifts in response to those stresses. When you apply different stressors to the soda bottle, will our soda remain fizzy or will it turn flat? In this simulation, I'm going to be applying different stresses, and at the side we have the mass action expression for this reaction. Notice that this is the equilibrium reaction written below, where you have H2CO3 decomposing into CO2 gas and liquid water on the right. So the forward reaction is a decomposition reaction, and the reverse reaction is carbon dioxide plus water yielding H2CO3. Notice that we have H2CO3 in aqueous form, carbon dioxide as a gas, and water as a liquid. Remember that liquids do not factor into mass action expressions, hence why you don't see it up here. The KEQ value, or the equilibrium constant for this reaction, is 30. So let's go ahead and apply one of our stresses. This is a 350 milliliter bottle, and inside what you will see are different colors representing the different reactants and products. What I will do is I'll show them in their molecular form here so that we can get a good visual. So let's see what happens. What will happen is when we decrease the pressure on this system. So right now it's at 2 atmosphere. By decreasing the pressure, I will just turn the cap off and release some of the pressure in that system, and then I will return the cap. And in that process, make note of what is happening. So I'm going to reduce the pressure to 1 atm. And let's take a look. Releasing the pressure, return the cap. Now, even though the concentrations of our CO2 and our H2O changed, the ratio changed in such a way that it kept the KEQ value at 30. So you're going to have to explain which way the system shifts in response to that reduction in pressure and why. The next variable that I am going to alter is the volume. So in this case, I will just set the pressure back to 2. And what I'm going to do is I'm going to increase the amount of CO2. How do I do that? Well, there are carbonation machines that you can buy that people actually like to carbonate their water and add flavorings to it. So just as this machine does, I'm going to inject some carbon dioxide into this container and take a look at what happens. So carbon dioxide concentration goes up. Which way will your system shift in order to alleviate that increase in concentration of CO2? Okay. The last stressor that I would like to apply is temperature, and I'm going to increase temperature, and this time I will show you a little bit of a graph, and this will help you determine whether this is endothermic or exothermic in the forward direction. So we're going to increase temperature of the pop, and let's see what happens here. So we've applied the stress, and I notice that carbon dioxide concentration is going up, and the H2CO3 concentration is going down, and eventually a new equilibrium is established. Notice this time the KEQ value did change. So temperature is the only variable that causes your ratios to be altered and creating a different value in KEQ. All right, so that is our simulation, and we are now ready to go answer some of the questions.